Okay. Good morning, welcome to Osservatorio now. The Catania section of INGV. I have the pleasure of introducing Dr. Anthony Lomax, who will hold a seminar, which is the fourth seminar in the frame of the celebration of the 25th of INGV. Before giving the floor to Anthony, first I will read a short biography. Dr. Anthony Lomax was born in Manchester in the UK and he grew up in Los Angeles. He received his bachelor degree in geophysics from UC Berkeley in the early 1980s. After a couple of years working for a private company in exploration geophysics, he joined the seismographic station of UC Berkeley in 1984 as a staff technician. In this time, he implemented the very first database to archive the data acquired by the Northern California Seismic Network, run by the seismographic station. In 1986, he started graduate school and he received his PhD from the University of California in 1992 with a thesis in which he developed a novel methodology to generate synthetic waveforms using Huygens principles under the advice of Bruce Bolt. He then spent a few years as a postdoc with Roel Schneider at the University of Utrecht, a few months of International Center of Theoretical Physics in Trieste in 1996, and then he moved to GeoAzur in Sofia, Antipolis, as a postdoc with Jean Verrieux within an EC-funded program. During this time, he started developing the first version of the non-LILOC global search methodology and the seismicity viewer softwares. He started to work as a freelance seismologist in early 2000. Anthony's interests cover a very wide range of topics that target the understanding of earthquake phenomenology. To this end, he has developed novel techniques to perform earthquake location at high resolution with the goal of better understanding the rupture process in time and space. He has started working with INGV since around 2000. Noteworthy is the development of the Early East Global Earthquake Location software that is used by the Central Delta Tsunami of INGV, and the introduction of the MWPD, a peak triangulation magnitude, for very big earthquakes, which has been found particularly effective for tsunami alerting in conjunction with the calculation of the little tsunami discrete parameters. More recently, Anthony has been working on high-resolution earthquake catalogs for the entire region. Now we can start with the seminar entitled A New View of Seismicity under Mount Etna Volcano, Italy, 2014-2023 from Multiscale High-Precision Earthquake Relocations. For those who are streaming and would like to ask the questions to Anthony at the end of the presentation, it's necessary to fill out the form provided within the presentation. So we can start.
Grazie. Buongiorno a tutte e tutti. Mi piace molto essere qui per le 25 anni di INGV. And I also very much like to thank Tiziana, Betty, and Ornella for this collaboration since 4 months, 6 months to resulting in this presentation and the paper. And I'd like to thank Paolo Montone and Diana Latorre for also organizing my visit, and the staff of the Annals Geophysica. Very pleasant procedure of preparing a publication. And also Alessandro and Boris for taking me around, and much of the way up Etna, seeing this magnificent place and the incredibly dynamic and changing environment, and a very, very beautiful natural environment too. And I'd like to thank everybody here too at the Observatorio. So my first thought when I was asked to make a presentation for the 25th anniversary was, why me? So I made a word cloud of my co-authors for papers from something like 40 years. And I thought, okay, that explains some of the reason why I might have been selected. So I'd like to show a few of the papers that I've worked on with Italian co-authors over also over many decades. So first is the seismogram analysis and earthquake location, including my first publication with Alberto Michelini in 1988. And also a couple papers where you see non-Lin-Loc, because the part of the focus of this talk is non-Lin-Loc and extensions of non-Lin-Loc. With the group in Naples, earthquake early warning. Also earthquake location in a sense, but a very different angle to do it very quickly for early warning. The rapid magnitude and tsunami warning algorithms and software, which became the earliest, as you just heard, and system that's still running for many years in Italy. Advanced earthquake location in general, which of course involves this algorithm non-Lin-Loc. Machine learning more recently, which does not involve directly the earthquake location, but a fascinating field. And we did work on machine learning for the localization of earthquakes, but a completely different approach than non-Lin-Loc or other standard earthquake location programs. And of course, volcano seismicity, including early work on Tomovez on Mount Vesuvius about 25 years ago. And on the lower left is the paper, which is one of the first applications using non-Lin-Loc. And we were able to get what we think is a more precise, more concentrated image of where the seismicity is under Mount Vesuvius. And then most recently, a study of the Campi Flegrei region. And there you see it's now called non-Lin-Loc SC. And that's the focus of the talk today, is application of this extension of non-Lin-Loc. And I'll explain what the SC is. And finally, there will be a paper from the work we've done this summer and what's in this talk. So first, what is this non-Lin-Loc SC? It's non-Lin-Loc SSST coherence. It's two extensions to the non-Lin-Loc standard location to greatly improve multi-scale and fine-scale precision of earthquake locations. I'd sort of like to remind you that much earthquake location still is based strongly on arrival times, picking arrival times, the arrivals of seismic energy on seismograms. And this basic methodology still forms a foundation and framework for earthquake monitoring and research, and including earthquake early warning. The non-Lin-Loc SSST coherence, non-Lin-Loc SC, is therefore still mainly based on arrival time pick data, the usual information that comes out of a monitoring network or observatory. And of course, it's based on non-Lin-Loc. Non-Loc is a probabilistic global search location algorithm, and it's particularly robust to errors in models, in the model used, and arrival time picks. So I'd like to just mention two aspects of non-Loc that are very important in general for earthquake location, and also are important when non-Loc is used in conjunction with the non-Loc SC. This first is that non-Loc does probabilistic global sampling to find the best locations to locate an earthquake. And it does this with something called octree sampling, which turns out to be a very, very efficient method to get a fairly complete image of the solution to the problem in three-dimensional space. And the result of that is a location probability density function, location PDF. So that's the yellow dots on the right. And these dots, this cloud, forms the complete solution. That's really the solution to the problem. And then after that, we may choose a certain point to be the hypocenter, for example, this purple star. But keep in mind, the complete solution is always this big cloud. And this cloud maps the full uncertainty of the location in 3D space. Second aspect of non-Loc, a bit more complicated, is that it uses something called the equal differential time misfit function. And the main power of this methodology is that even if there's some bad data points, some bad picks for some reason brought into the location problem, this EDT methodology is very, very good at identifying and removing any bad effects of these bad data. So here's, it's a synthetic kind of toy example of a location which uses 6 readings, but one of the readings has been perturbed and given an erroneous value that's 10 times the nominal uncertainty that's used in this location procedure. So the upper diagram shows what happens with a standard location program, which is sometimes called RMS L2 least squares. And the solution, the correct location is the green square, the green cross. And the solution that the standard location method gets is biased, the yellow star, and also the uncertainty information in the standard location method, the blue contours, does not even contain the correct solution. And basically, these methods are trying to satisfy all the observations without any regard to whether the observations are good or bad. In the case of the EDT, you get a much more complicated solution, which is represented by all these blue contours again. But in most cases, the optimal solution, the best point in this solution space, will stay in the correct place near the solution that is correct for the data that is not erroneous. So it's able to remove the erroneous data. Effectively, the EDT method satisfies the most pairs of observations, and it doesn't mind ignoring some observations. So we have a global search method that gives these complete PDF representations of uncertainty, plus we have a methodology that allows to have some noise in the data. So on top of this, we add the 2 components of non-Loc SC. The first component is to improve the multi-scale precision of the locations, the intermediate scales and larger scale. And this uses something called source-specific station correction terms, non-Loc SSST. And what it produces is 3D maps of corrected travel times for each station and phase. So normally, quite commonly in earthquake location, we use what are called static corrections, which is a single correction for earthquake location. In this case, it's an extension of that, but it'll be a map in 3D space, which I'll explain a little bit more. The second component of non-Loc SC is non-Loc coherence, and this greatly improves small-scale precision by taking advantage of the fact that nearby events, nearby earthquakes or other seismic events, often have very similar waveforms. And I'll show how this helps us to also improve the locations. So the first component, the non-Loc SSST, it's an iterative procedure which starts with standard locations. that you may get with some velocity model. And then it examines the residuals from these locations, the errors between the predictions of picks given by the locations, the error between those predictions and the actual observed predictions. It iteratively examines those residuals, and in this first step, it makes corrections which are just one value for each station and phase. So the plots here on the left, they show the correction field, which is constant at the first step. And on the right, it's the travel time field in 3D that we will be using to locate in the next iteration. So in a later iteration, we do the same thing. We'll be examining the residuals from locations done with the results of the previous iteration. But in order to make corrections now, we do not have a constant throughout the 3D volume, but we average the corrections within a certain distance from each point in the volume. So effectively, we're finding corrections that are specific to each possible hypocenter point when we might do the final location. So it's a variable field of travel times. And so it's an extension of what I referred to earlier, the constant station statics to smaller spatial scales and a non-constant field. And then by a final iteration at some scale, you'll have quite a complex field of corrections, and the corrected travel times may start to look quite irregular. And also another way to think about this procedure is it's very much like 3D tomography, using residuals and iterating to correct locations and, in this case, travel times. But there's never a velocity model in this procedure after the very initial model we use for the first locations. So it's something like tomography, but not quite the same. And I hope in the future be able to explore the differences and advantages, disadvantages of the two approaches. The second component of nonlinear SC is nonlinear coherence. And it's been known for a long time that events with very similar waveforms up to some frequency have very small separation in the Earth. The hypocenters of events with similar waveforms should be very closely located. So this has been used for a while for various purposes, but in particular for high precision location. And on the two panels on the right, there's a study quite a while ago by Marco Cataneo et al. And you see sort of initial locations, and then taking advantage of these waveform similarity, they're able to get differential times, very precise differential timing between nearby earthquakes, and then do relative locations which take advantage of these differential times. Two procedures that are widely used now that use this basic algorithm are HypoDD and GROCLUST, which I will be mentioning some more. So nonlinear coherence does not use the differential times between similar waveforms. What we have is for each target event, that's each event in the catalog we're relocating, we take its waveform and then we find all other nearby events that have very similar waveforms. And we then measure, that similarity is measured with a coherence, which can vary from 0 to 1. And in this case, we will use, we'll only use waveforms that are similar to a measure of 0.5 coherence. So we have our target event, its waveform, and nearby events that have very similar waveforms. We next convert the coherence to a weight from 0 to 1, and the target we're trying to relocate always has a weight of 1, of course, and then other events may have some value between 1 and 0. And then we've relocated all of these events previously in our nonlinear SSST stage of processing. So we take the final location PDFs from the SSST location, and we are now going to combine those, stack them together using this coherence-based weight as a weight. So it's a weighted stack. And doing that, we typically get something, this is of course kind of a cartoon, but we typically get something like what's shown here. The combination gives a new location for the target event, which typically has a much, much tighter, smaller probability density function. So it's a much better constrained location. And basically, I've been using this now for, I don't even know, maybe 3 years, 4 years. And in general, as I will show in some later figures, the final precision that's achieved by this methodology is very similar to what's achieved by the commonly used differential timing methods, HypoDD, GROCLUST, and others. Well, that I'm sure was very complicated and didn't make necessarily a lot of sense. So I have more of a graphical way of showing what this procedure is doing. So if you consider this picture to be the true earthquake locations that we'll never know, but the true earthquake locations that we're trying to relocate. If we do standard catalog locations, we'll get something like the image shown here. There's two primary types of problems here. There's the multi-scale epistemic distortion, the larger scale and intermediate scale distortion of the image. Plus, there's a intermediate to smaller scale blurring, aleatoric blurring in the figure. The larger scale and multi-scale distortion is typically due to having an incorrect velocity model. We never know what the true Earth really is, and we never have the correct velocity model. So that introduces distortions. And the blurring is also due to many sources, but in particular, the noise in PICs. Basically, when we measure anything, we have some kind of uncertainty and errors. So the combination of those two might give something like this image. Now, these procedures that are commonly used, like HypoDD and GROCLUST, in many, many papers, people start with the catalog locations, and then they apply HypoDD and GROCLUST. So that's a very powerful method, especially for the small scale errors and blurring. It gives very good results for fine scale precision, but it does not directly address the multi-scale distortion. So I sort of give, in a cartoon way, show this as a figure where the larger scale distortion is still there, but there's very, very good fine scale precision. Okay. The non-Linloc SSST coherence, in large part because of the SSST step, is giving something that is addressing both the multi-scale distortion and the improving fine scale precision. So I have a cartoon figure here, hopefully representing somewhat accurately, but the kind of results you can get. Though I will say it's probably a bit optimistic on the larger scale distortion. That's a very difficult problem when you don't have information about velocities in the Earth. So I'll now just show a first overview of application of non-Linloc SC to the Mount Etna seismicity. First of all, there's a fabulous station network around the mountain, and particularly in the central crater area, there's a large number of stations. So it's a very good geometry for earthquake location and very high quality pics and data. We're also using stations further away out to the Aeolian Islands and further in Sicily and on the main Italy. So this is the INGV Observatorio Etnea catalog for the 10 years we're looking at, 2014 to 2023. So you can see there's quite a bit of structure already, and there's clustering of earthquakes. I'll show many figures where there is a map view on the upper left. Below, there's a profile view from the south showing all earthquakes. It's not a section. And on the right, there's a profile view from the east, again showing all earthquakes, not a cross section. So memorize this picture, please. And I'll show the initial non-Linloc locations. So these will be roughly equivalent to the INGV locations in that they're just a fixed velocity model, locate the earthquakes, but done with non-Linloc with its various special features. So there's a little bit more concentration and organization of seismicity, a little bit less blurring, especially at depth. But it's very, very similar locations to the INGV catalog. The next figure I'll show at the end of the SSST iterations. And here you'd see quite a dramatic difference. And so there's increased clustering and organization. And if you look carefully, or I can go back and forth, I'll go back and then up to the SSSD. There are some larger scale, intermediate, larger scale shifting of concentrations of seismicity. And then finally, I'll show the coherence after the nonlinear lobe coherence step, where we've used the waveform similarity, and you'll see a dramatic difference. So the main difference here was on a smaller scale, that the clusters and streaks and alignments of seismicity collapsed quite a bit more, but also some of the larger scale fuzz was reduced with the coherence step, because coherence can take an earthquake that's badly located, and because of waveform similarity, it can pull it into the cluster of earthquakes where that earthquake really belongs. Before looking at a little more detail at the Etna seismicity, I'd like to show some work I've done recently with Pierre-Henri from Marseille, which illustrates well why I think this multi-scale location precision is important. Not just having the fine precision, but also having a larger scale, multi-scale precision. So basically this work was relocating earthquakes along major California strike-slip faults, mature strike-slip faults. And part of the results we got showed that the faults are very smooth across multiple scales. They're not particularly rough as many studies consider them to be. So this is the central San Andreas fault, the Parkfield segment, where there are magnitude 6 earthquakes roughly every 20 years. And the seismicity shown here is I think a 40-year period, but it includes the 2004 magnitude 6 Parkfield main shock and aftershocks. These earthquakes are located by the Northern California seismic system with a semi-automatic, near real-time use of hypo-DD. So these are the relative locations done with waveform similarity and differential timing, high precision differential timing. And they've got very nice definition of thin organization of the seismicity along the San Andreas fault. However, you might notice that there are sort of kinks and bends and offsets in the seismicity, particularly on the left, on the map view, you can see. The view on the right is looking from the right side along the fault in a kind of perspective views. When we apply nonlinear SC to this, we get a similar fine scale organization and clustering of seismicity, but you may notice that the larger scale organization for nonlinear SC is very planar in both the map view and in the perspective view. It's near a plane, and in fact, given the uncertainties of the final locations, the seismicity is fit by a perfect plane. So we're saying that the multi-scale precision of nonlinear SC relative to a procedure that is mainly improving fine scale precision, the multi-scale precision is perhaps giving us information about the true smoothness and shape of the fault. In this case, planar within the results. And we would say that perhaps these kinks and offsets are not representing the true fault. So we have a planar fault, and that would be a very, very smooth. Nothing is much smoother than a plane. Another example is a little further north along the Calaveras fault. So I show the same things. I show the Northern California seismic system hypo-DD relocations. Again, very, very, very nice fine definition of features in the seismicity. And still there are some sort of kinks and offsets in the seismicity. And relocating the same seismicity with nonlinear SC, we get, again, a smoother alignment of seismicity along the fault. particularly around the aftershock sequence of the 1984 Morgan Hill earthquake, 1906.2, which are the red dots you could see. And in this case, our interpretation is that the non-Loc SC is imaging, in fact, a smooth curve, and not just a smooth curve, but it's well fit by an arc, so a semicircle. So with the addition of multi-scale precision into earthquake location, we're finding for these mature strike-slip faults in California that the rupture surface for moderate-sized earthquakes and other parts of the fault is very, very smooth on larger scales. Why might this be important? Well, simply because a planar surface or a simple arcuate surface, a very smooth surface, can move without geometrical impediment. There's no masses of rock that have to move through each other or destroy each other when an earthquake occurs. So in this case, this would facilitate and perhaps make possible nucleation and propagation of extensive large earthquake rupture. So I find that to be a nice result, a nice proposition based on the fact of having the ability to do multi-scale precise earthquake location. So now I'll look a little bit in more detail about our results for Mount Etna. So in general, if we start with the initial, not non-Loc initial locations that I showed, but the INGV locations, which are fairly similar to the non-Loc initial locations. And then we compare to the final non-Loc SSST coherence. There's a lot of organization on multiple scales, clustering, and linear features in the seismicity after a non-Loc SC location. One area where this is quite clear is the shallow seismicity, or the seismicity above about 10 kilometers in the central crater area, where it collapses into a number of fairly tight clusters and then some other more elongated features. So I'd first like to look at, try to look a little more at the shallow seismicity and give you an impression of what non-Loc SC might be doing. So on the left here, I have from Alperoni et al. 2020, what is probably some of the finest locations of seismicity on Etna, because in this case they've used a tomographic 3D model plus a hypo-DD code that runs in a tomographic model to relocate these earthquakes. And I've tried to, that's a figure from the paper, and on the right I've tried to reproduce kind of the same picture, the same colors, the same scale with our non-Loc SC results. So overall, they are very similar. They're both quite fine, detailed locations of seismicity. This is for only 2 days, December 24 and 25, which I think most of you here are extremely familiar with. Days of high seismicity during the 2018 Etna flank eruption. And the yellow line shows an eruptive fissure at the surface. And quite interesting is both sets of locations show seismicity at north and south of the eruptive fissure and basically nothing along the fissure. If we look a little closer, if we examine the summit seismicity, they're very similar, but there is a suggestion in the non-Loc SC relocations of a little less extent to the overall seismicity in the summit area, and the possibility, the suggestion that there are really only a few clusters and they're very, very tight, where the seismicity is coming from. And further south, or just to the south, but on the southern boundary of the Vallée de Beauvais, again, the seismicity in both cases is very similar, but there is some suggestion that the spread of seismicity in the non-Loc SC relocations is tighter, particularly, say, the north side seismicity just south of the eruptive fissure. But something I think more interesting is that the non-Loc SC relocations are showing an organization, a sort of curved trend along the southern boundary of the Vallée de Beauvais. And so that's something, of course, we have to look in more detail at, perhaps try to improve the locations for this area. Of course, look at mechanisms and other information. But I find that to be an intriguing result, which would be the kind of thing you'd expect to find with this multi-scale relocation procedure. A couple more things. The shallow seismicity on the right, it shows shallow seismicity above 2 kilometers below sea level. And on the left, a zoom into the seismicity around the Mount Etna. And along the Pernicana fault system, the non-Linlock SC relocations give quite a linear trend for the eastern 2/3 of the seismicity along the fault system. And then there's a change to the west, the 1/3 of seismicity to the west, where the fault bends into the northeast rift. But if we look at the depths of the seismicity along the Pernicana fault system, the non-Linlock SC relocations are showing pretty much a vertical plane for the 2/3 of seismicity to the east. And the 1/3 of seismicity to the west, which is mostly earlier seismicity, shows a dipping plane to the south-southeast. So again, that's something to do more investigation, of course, but it's also an intriguing result that is a consequence of both multi-scale and the finer scale precision of non-Linlock SC. On a larger scale and at greater depth, one of the types of features that comes out with the non-Linlock SC relocations are dense, elongated clusters, deep clusters. And these, some of these occur at the same time as intrusions and eruptions on Mount Etna. So they're generally considered to indicate something to do with magma movement at depth. So again, more work needs to be done to decide what would be the relation, because you can't have earthquakes inside magma. So it has to be something to some geometrical relation to a movement of magma. But in this case, you can see the extremely dramatic difference between the INGV catalog locations at these depths and then the definition of these filaments, these streaks and tight clusters of seismicity. And finally, something I think quite interesting. It's been observed before, but I think there's a clearer definition here. This is a view, a profile view along a perpendicular to a section that is aligned along to the northwest. And so the deeper seismicity between the arrows is actually mostly falls on a tabular plane dipping to the northwest. So the bulk of the seismicity is on a fat plane, which is probably related to larger scale tectonics, crustal conversions, not directly to an Etna volcano. But I think the definition of this as a clear planar surface seems, again, an intriguing and important result. The two of the filaments, dense streaks that I showed earlier, are present in this section, and they are not within this plane, which is also another interesting feature of the result seismicity. So particularly the filaments that are related to magma movement, it kind of makes sense that they may not fall on a plane of seismicity that's due to longer term tectonic and geologic structural features. So I want to have one more illustration of why I think multi-scale location precision is important, as opposed to just very fine scale location precision. So here I will show some very recent work I've done that's all very preliminary, but it basically says that finite fault slip for larger earthquakes, the actual rupture of a larger earthquake, where it occurs, how it fills the fault, can be mapped from seismicity. And I'll explain how this is done, but this procedure also depends on multi-scale precision of locations, that on intermediate and larger scale, the positions of earthquakes are well resolved. So this actually uses a procedure that many of you will be familiar with, certainly all seismologists, but there's something called Coulomb failure stress, which has to do with cracks and faults and so on. And basically, when there's a large earthquake, this Coulomb failure stress could be calculated corresponding to the way the large earthquake ruptured. And the pattern of this Coulomb failure stress in 3D indicates where you are more likely or less likely to have aftershocks. So in this classic example, the red zones, red and yellow zones are where we expect more aftershocks, and the blue zones are where we would expect fewer aftershocks after this magnitude 6 earthquake. And in fact, I think you can see here, it's not perfect, but there's a good correlation between the denser areas of aftershock occurrence and the pattern. This has been used quite often on Etna and many other places to, given a dike intrusion, calculate the Coulomb failure stress field, and then discuss that with regards to the earthquakes that occurred after the dike intrusion. In this case, earthquakes on the east slope of Etna on the shallow faulting systems. So all of that is what's called the forward problem. We have a strain occurrence, an earthquake, a dike intrusion. We have this Coulomb failure stress physics, which we use, and from that we predict where seismicity may or may not occur. So I think that raises immediately the question, if given the seismicity that occurs after an earthquake or an intrusion, and the physics of delta CFS, Coulomb failure stress, can we image the main earthquake rupture or intrusion geometry? So this would be the inverse problem, taking the seismicity, using the Coulomb failure stress physics, and trying to map the strain field, the strain object that created this seismicity. Well, it actually seems to work fairly well. This is again back to Parkfield, 2004 earthquake in California. The yellow dots are aftershocks for the first 4 hours after the magnitude 6 earthquake. And the red and blue field is the point source for Coulomb failure stress for a right lateral strike slip fault oriented along the San Andreas fault. So we have these two components. We have our point source Coulomb stress change for a strike slip fault. We have our aftershocks. And what we do is we very simply correlate the two. We move the point source over the 3D distribution of aftershocks and just measure how well they correlate. That is, how many of the aftershocks fall in the red zone where we expect aftershocks. And we give a penalty if aftershocks fall in the blue zones where we don't expect aftershocks. So, nice. So that was a 3D correlation of a 3D object with an aftershock distribution. The result is a kind of blurry map. It's an image of where faulting may have occurred in this earthquake. You can see the main shock hypocenter is the red star, and then the faulting extends through to the northwest through the aftershocks. And so what we've actually done here is we've used the aftershocks as virtual sensors, as virtual stress sensors, and backing up from that with some assumptions about faulting mechanisms, right lateral strike slip in this case, we map an image of the places where the fault may have slipped. So virtual sensors in 3D at depth is quite nice because in geophysics we have very few instruments deep in the earth, usually none. It's also important that in this case, there was never a specification of a 2D fault surface where we want to map the slip. But most of the procedures that do finite fault slip, they have to fix a 2D fault surface. So if we compare this result to, here's 3 finite fault maps produced for this earthquake, the match is pretty good. It's very similar. Also, given that finite fault maps, when there are many finite fault maps produced by different groups, they show a large variability. So within the kind of typical variability of finite fault maps, this simple imaging result is producing something quite compatible with previous results. So now if we come back to Etna, another result we've had with this relocation study, but this has previously been seen, is that the p-axes for the faulting for the earthquake mechanisms are generally radially distributed around the central craters, around the summit of Mount Etna. It's actually very well radially distributed, except for some of the deeper earthquakes to the northwest. So this is suggesting that it's not suggesting, it's actually known that there's a strain source. There's intrusion under the central summit, around the central summit, but nearby, so that the orientation of faulting mechanisms is such that they're responding to this radial stress field. So can whatever the intrusion geometry is in 3D be mapped from the seismicity we relocate, and again the physics of Coulomb failure stress? Well, there I have not really done much work, but I've just tried a couple examples. So I'm showing here is what I call very preliminary, because I am modeling here an opening fissure, an opening crack, an opening vertical dike. So it is a volcanic inversion, or a mapping using volcanic physics for the source. However, at the moment, because of the limitations of the code, I'm using more earthquake-like assumptions for the aftershocks. So there's already something that needs to be improved. But when I go through the process that I just showed you, I get this map, this 3D map of potential intrusion geometry shown in cyan, in bright blue here. But that's about as far as I wanted to go with this, because I just wanted to see if anybody's intrigued or has any comments. But it could possibly be a potential additional tool for monitoring volcanic activity, and in particular the geometry of intrusive activity. I'll stop there without a big conclusion slide, but I'll leave you with an animation of the seismicity I've shown, 3D perspective view. And if there were certain points that I made that particularly interested you, you may be able to see them more clearly when in this animated rotating view. Because in my opinion, can't understand seismicity if you don't have an interactive 3D view. And also time. The colors here represent time, except for the blue cloud in the middle, which is the image map I made of the intrusion. Thank you very much.
Thanks a lot, Anthony, for this very interesting presentation. And I have a question before looking at other people who may comment or ask you questions. Is there any minimum threshold in magnitude for your method?
No, as long as the earthquake is able to be recorded over background noise and pics can be made. Mm-hmm. That's for the initial locations and the SSST procedure. So it's just like any other location study. If you can pick arrivals, you can locate.
Okay.
For the coherence part, the same thing really. The waveforms have to be not too noisy. So if the events get smaller, you lose stations. But if you have closer stations that are recording waveforms with good signal to noise for a small magnitude, you can use those.
Yeah, and what about the phases during which we have an increasing volcanic tremor? You know, it's a problem for us.
I think it's subject to the same limitations as other methods. Yeah, because it fundamentally relies on the peaks. So it has to be volcano-tectonic earthquakes with onsets. And if the tremor comes up, you're getting what we would call noise. Though I think tremor, I'm learning tremor is one of the most important indicators of what's going on. So it's not noise in the greater sense.
All right. So, is there any question here? No. I don't see any question from those who are connected in streaming. So, no comments, nothing.
Can I ask a question?
Yeah, sure.
Does anybody have any comments on the deeper, what I call filaments or very concentrated clusters, but they align typically subvertically and in very dense.
Marco, please come here. Tell your name, please.
My name is Marco Firetto. Nice to meet you. We made a work in 2002 analyzing seismicity from 2005 and 2019. And we saw the same situation. It was localized with the TomoDD. And we saw this northeast southwest strike and northwest sinking seismicity.
The larger scale.
Yeah, this scale.
No, you're talking about the larger scale dipping surface.
Yeah.
I was wondering. Oh, okay. Well, that's it. I was also wondering about these tiny.
I was
okay. Okay, good.
That well, we relate to the subduction of the Iberian foreland within the Etna, and about this, it should be related to a fault, which is probably linked with this.
Okay. You think there's a relation?
This is not. This is just
an
idea. Okay, a fault which should go outside the Ionian Sea.
Okay.
So it's something that connects with the upper seismicity. This is one idea. Okay, but we are just still working on this.
Because in this case, not all of them, but at least two of these dense clusters are correlate in time with eruptions or movement. And the other thing is, in other volcanic studies I've done, these often show up around dikes. So I was favoring something to do with magma movement, dike fracture opening. But
we think that this sinking volume may act as a mechanical boundary to intrusion. Yeah. So when the magma rises up, it pushes and breaks. Okay. So this is one interpretation of this. If you are interested, I mean, we have similar locations with TomoDD, and there is a very interesting structure in this place, but it's too long to talk now.
Yeah.
Okay? So if you're interested, we can see later.
Yeah. Okay.
Thank you very much.
Have you analyzed only the 2018 eruption, but not
well, this is a 10-year period. So, so there are other eruptions, intrusions and eruptions in the period. Yeah. I think we have one other 2000.
Yeah, 2021 was a baptismal event, but
no flank eruptions.
No flank eruptions, just the 2018. Yeah.
And what about this these episodes? I mean, is there any change between the flank eruption in 2018 and these summit eruptions? From your point of view.
Let's see. Well, 2018, what I showed, and I think what we focused on was more towards the summit, the seismicity.
Yeah.
And the boundary of Valle de Bouc. So I don't know that I have any answer to
have you found
lateral eruption versus
recurrence of families, for example?
We haven't looked at things temporal. However, that has, I'm sure, been done. these relocations don't add much to a sort of a temporal time series. Except, for example, if you're studying depth, if the depths here are more precise, then if you're looking at depth over time, for example, this may give some clearer information. But the overall relationships of where seismicity occurs and when on a general scale, I think this would not give more information than the standard catalogs.
Just a comment, maybe
Please
the
come here, Betty,
maybe
and say your name here on mic.
Okay, I'm Elisabetta Giampiccolo. No, just a comment. Maybe the deeper clusters. The deeper clusters are maybe linked with the uprise of magma from that. And for example, for 2021, we had uprising of magma from that. So above all, we are investigating this aspect, but this is an interesting result.
An indication of a recharge.
Yes, recharge from that. Thank you.
Thank you. All right. No other question. I don't see any question from the web. So thanks a lot once again.
Thank you.
And thank you for coming here for this special event of INGB. So thank you for your attention and see you. Thanks a lot.
Thanks. It's just exactly 1 hour.
Yeah.
Typing was good. I never do.
Is it the first time?
And